Part 4, this is for questions 31 to 40. Question 31, butane 2-on reacts with alkaline iodine and aqueous of dilute sulfuric acid is then added to the reaction mixture. The organic products of this reaction sequence are triiodomethane and product M. Then what is product M? Now what happens, there are two processes here. So first of all, butane 2-on is CH3. Then there is a carbonyl here. And then butane 2-on, so we need CH2 here, and then the CH3. So for a positive result, we must have CH3, then CO. Okay, this group here has to be there. If it's an alcohol, then it has to be CH3, and then COH, then with the H. Okay, and then any other that comes. So now for one alcohol, then this one is first oxidized to the ketone, okay, and then the other process continues. So what happens in the reaction here with alkaline iodine, they are going to first replace the hydrogens here, okay. We replace those hydrogens. We have now C3 like that. So I mean CI3 and then the rest. So these hydrogens that are on this methyl group that is attached to the carbonyl, they are replaced. Then after that, hydrolysis takes place. So in the hydrolysis of this one using the sodium hydroxide, because it is alkaline here, what is going to happen, we are going to see that you cut off this one here, and then you form that triiodomethane, okay. Then when you cut off this one, it is oxidized here. Then you are going to have something like, this is CH3. So I'm beginning from this side, then CH2, then COO minus, okay. Let me show you in the book how they show it actually. So when I come to my book here, and then I open carbonyl compounds, that is chapter 18, then we go triiodomethane, this iodoform test, where is it? I think it must be around here. So this is the one here. Step number 1, the carbonyl compound is halogenated. The 3 hydrogen atoms in the CH3 group are replaced by iodine atoms. You see? That is exactly what I've shown you there. So if you look at what is happening here, let me try to zoom. All of these hydrogens here, they are replaced. Then after that, hydrolysis happens. So you are going to have, so I cut this one off. So first cut off this carbon here with the 3 iodine atoms, and then you give it a hydrogen. Then you have the triiodomethane, which happens to be the yellow precipitate, okay. Then the remaining part will be the salt, okay. That organic salt you're going to get there, this one here. So I'm putting off the sodium, and then I'm leaving it with as a conjugate base, okay, because it can receive a proton. Now when you add sulfuric acid, you can get that what? Proton back. So I'm going to have this one here now coming to CH3, CH2, then COOH, because here they said add an excess of dilute sulfuric acid, so you will get out the propanoic acid. You see that? So propanoic acid is actually option what? D. Then question 32, they are saying that 4 reagents are listed here. We have aqueous potassium chloride, dilute hydrochloric acid, then liquid thionyl chloride, and then we also have solid phosphorus pentachloride. Which reagents, when added to ethanol, will rapidly produce a gas that turns blue litmus red? So this one that turns blue litmus red must be acidic, an acidic gas. Now we have a reaction here with thionyl. alcohols can react with these two in a substitution reaction, and then we get alkenes. Okay, like if I have ethanol here, CH3, CH2, OH, then can react with this thionyl chloride, and then we get CH3, CH2, Cl. This one is substituted, and then we are going to also get HCl. This one comes off as a gas, and then also that is sulfur dioxide. Now this one is an acidic gas, and then this one here is an acidic gas, so they can turn the blue litmus what? Red. So that means this one is there. How about with solid, this one, phosphorus pentachloride? So phosphorus pentachloride. Again, let me show you in the table, in the book actually here, so that you see this very well. Now I will go to alcohols. This one has to be in alcohols, chapter 17. So alcohols here can react with, I think I can continue. Yes, here, PCl5. Do you see this? Actually, it is ethanol. It is the same that is there. Ethanol. You can see HCl here, and then POCl3. So if I can go back here, I'll put the CH3, CH2, then Cl, and then plus HCl, then plus POCl3. You see that? Now, this simply implies that, again, this is an acidic gas, so it can also give us, okay? How about dilute HCl? Is it there? Even with dilute HCl, it is there also. Alcohols can try to react with the acid here. You see, chloroethane. You can get the chloroethane. They are actually bringing things that are there in the book. So we also have this one here, CH3, then CH2OH. You add the HCl, and you will get CH3, CH2, Cl, then plus, what else? Is this one going to be water? Yes, if it is water, I think it has to be one molecule of water. They must have made a mistake here in the balancing. So that is that. And of course, for this one, it is not there. That reaction isn't there. So the gases that are turning the blue litmus red, that are acidic, we are seeing from option 3 and 4, and therefore the answer has to be D. Then question 33, 4 drops of 1 chlorobutane, 1 bromobutane, and 1 iodobutane are put separately into 3 test tubes containing 1 cubic centimeters of aqueous silver nitrate at 60 degrees C. In each case, a hydrolysis reaction occurs. This is what is happening. So we get an alcohol there. Okay. In other words, this CH3, we have CH2, CH2, then there is CH2 here with a Br. Then we are also having another with the iodine. Then we are also having another with the what? With the chlorine. You see that? Now they are saying that R represents this butyl group and X represents the halogen. So the R is actually this butyl group. This whole thing here. Okay. Then X is the halogen. The rate of formation of the cloudiness in the test tubes is in this order here. Now the cloudiness is going to be this one here. This is silver. So something is going to be broken off here. You will get silver bromide, which is a cream precipitate. So it will form that cloud, okay, with cream color. And then this one here, iodine, together with the silver, you get a yellow precipitate. And then chlorine, together with the silver, you get a white precipitate. You get that? Then after that, what are we going to have? The rate of formation of the cloudiness, that means we are looking at the bond strength here. Which of these ones, this one here, this one here, and this one here is the strongest? So the strongest, of course, is going to be with chlorine here, because chlorine is smaller in size, okay? And because it is smaller in size, we are going to see that there is not going to be a lot of polarization here. But when you look at this one of iodine, it is very large. So there are electrons here. The distance between the nucleus here of iodine and the bonding electrons here is too big. So what is going to happen is that there is going to be a weaker attraction of these bonding electrons, okay? So that weaker attraction will make it so easy to break this bond here. So actually what we look at is the bond strength. So as we go down the group, the bond strength actually decreases, okay? If I can take you again into this book to show you, it is exactly here. Let's go to group 17, which is here, and then we look at bond angles. It has to be bond angles as you go down the group of these halogens. Yes, you can see here the bond energies. Sorry, not bond angles, bond energies. So they keep on decreasing down the group. Now, you can see from this table here, yes, here we are using hydrogen, but replace it with the carbon. And look at the explanation here. They are saying the bond energies decrease going down group 17, making it easier to break this bond here, okay? I can say carbon to halogen bond. This is because the iodine atom is the largest atom, right? So the overlap of its outer shell with the halogen or carbon atom gives a much longer bond than with other smaller halogen atoms. So the longer the bond, then the weaker it is, and the less the energy required to break it. Hence, this with the iodine, okay, that carbon to iodine, for this case, is the less thermally stable. Okay, here we are talking about the thermostability, but bond energies, for this case, they are the ones that we are supposed to be looking at. Now, when you come here, why is it like this? Look for bond energy. The bond energy of Rx decreases from chlorine to that of iodine. So the answer has to be A. You don't even need to focus on anything else. As simple as that. Question 34. Propanoic acid reacts with lithium aluminum tetrachloride to give organic product P. Now, of course, organic product P, this one here is going to be, because this is a reduction reaction, we are going to have propan 1O. So we have propan 1O, which will reduce it to a primary alcohol. Then methanoic acid reacts with organic product P in the presence of a few drops of concentrated sulfuric acid. This one acts as a catalyst to give organic product Q. Now, this is an ester, okay, because we are seeing a carboxylic acid reacting with an alcohol, okay? So what we are going to have is going to be CH3, CH2, CH2OH. This is our P, then plus methanoic acid is HCOOH, and then what is going to happen, in fact, let me just put it like this. If I have this one here, the carboxylic acid, we have an OH here, okay, then so the carboxylic acid is going to lose the OH, and then the alcohol will lose the hydrogen, okay, and then water gets off. So it's a condensation reaction. You'll have the CH3, CH2, CH2, then O, then C, and then this oxygen here, and then that. So this one is called, the alcohol group is this one here, which is propyl. so we shall say propyl. Then this one, methanoic acid, so we shall say methanoate. Methanoate. Okay, that is our Q. So what do we have here? Organic product P must be propan 1O. So this is CH3, CH2, CH2. Okay, then OH. So we have A and B. Okay, we have A and B for propan. Propan 1O. So this one is off, propanal. Then we come to Q here. We have the carboxylic acid end is here. It doesn't matter whether we write it at the end here or at the start here. Okay, I can begin by writing it like this, then O, and then I put CH2, CH3. CH2 here and then CH3. It's the same thing. Now, look at if I look at this one here, because now this one is CH3, CH2, then COO. That means the carboxylic acid is propanoic acid here for Q. So Q is wrong. The carboxylic acid is methanoic acid. So it has to be this other side here. Do you see this? This is the carboxylic acid end, and then this is the alcohol end. So that means we are having our answer here. This one is okay. So that means the answer has to be what? B. Then question 35. Samples of gases, we have chloromethane and then chlorine are mixed together and irradiated with UV light. So the process here, the reaction is going to undergo free radical substitution. Okay, free radical substitution. Which compound is produced by a termination step? Remember, in free radical substitution, we have three steps. One is the initiation, where the chlorine here, this chlorine bond here is broken by the UV light homolytically. So each of them takes back the electrons it shared in this bond, and then we get two radicals. Then now that is initiation. Okay, then we begin with propagation. So in propagation, we actually look at this one here attacking a molecule. We are having a radical attacking a molecule. So it attacks this molecule here. Okay, actually what happens is that we get, I can project a hydrogen here, then you have CH3, it will be CH2 now, and then this. So this one brings this hydrogen, this one breaks off by doing that. Okay, so then you are going to get HCl, then plus. Now we are going to form another radical. You see this one here? It has received an electron from there. So it's another radical. So in propagation reaction, we see, in the propagation step, we see a radical reacting with a molecule to produce a new molecule and then a new radical. You see that? Then in termination, this one can go on and on. This one can again attack this molecule, the CH3Cl. They can go on and on. But when we get two, okay, when we get two radicals coming together, then we shall get what we call a termination. Okay, the reaction will stop when two radicals come together. So there is a possibility of having this radical and also another radical. So I can again put this one here, CH2Cl. So these two come and share those two electrons, and then you can get CH2. This reaction here is so reactive because these radicals cannot live on their own. Okay, because the chlorine cannot be there as an atom. That's why it exists as what? As a gas. They come and then share those two electrons. So there is this possibility here, and they are saying which compound is produced by the termination. We can see this one here. In here, we don't produce alkenes. Okay, We don't produce alkenes. There is a possibility of producing HCl, but it is produced in here in propagation, okay? But then we don't have where we are getting hydrogen as a what? As a radical, then plus the chlorine as a radical, then to get HCl. No, HCl is actually produced in here like this. So when a radical attacks this molecule here that has gotten the hydrogen, so the hydrogen reacts with that chlorine, and then you form the HCl. You see that? So that was tricky because in here we get the HCl, but it is not under termination. We get it in propagation. You see that? So that's why we have our answer as C. Then question 36. Propan 1O is dehydrated by passing its vapor over hot aluminium oxide to give a hydrocarbon. The hydrocarbon has to be an alkene. Okay? And this alkene, if this is propan 1O, then we are going to have propene. And they're saying which structure formula represents the product obtained when hydrocarbon reacts with bromine. So when you get propene, which is CH3, okay, then CH, I think we shall have CH, then double bond CH2. That is the propene. Then you add bromine. So when you add bromine, this one is what we call, it is called what? Electrophilic addition. Because you have bromine and bromine here. So as this one is actually uncharged, but as it draws closer to this molecule here, this one has a high electron density and electrons are negatively charged. So they will induce a positive charge on this bromine. Okay. And then this one will be a minus. Okay. They will repel the electrons around bromine, and then they will tend to move towards this other bromine. That's why they will attain a partial positive charge. And then this one comes in here, then this one goes, and it breaks off, then we shall get CH3, then CH, then CH2 here, then Br. Okay, so this one with the two hydrogens, we will first have the what? The bromine, such that we get a carbocation, a secondary carbocation, which is more stable than when we had, let's say, this one here, then CH2. This is a primary carbocation because there is one alkyl group connected to this one here. So secondary carbocations are more stable compared to the primary carbocations. And in that case, we produce what we call, they will produce the major, we get the major what? Product. And then now the bromine that is here is, that is broken off here, is going to be completely negatively charged. And then it will come to this one here, it will give it the electrons, and then we can have a CH3, then CHBr, and then CH2Br. Okay, so we should have the two bromines distributed on the two carbons that are in this double bond, and therefore our answer becomes a D. Question 37. Alkene S has molecular formula C4H10. S reacts with chlorine in presence of sunlight to produce only two different monochloroalkanes. This is again free radical substitution. So this is C4H9, then Cl. One hydrogen is replaced. Now remember, in free radical substitution, all those hydrogens can be replaced. Okay. Remember, we have the propagation step. They keep on, the radicals keep on removing a hydrogen from the molecule, and then it continues until when two radicals come together in the termination step to give you a product. But there are very many products that we can get from there because of the propagation. Both of these monochloroalkanes are treated with hot ethanolic potassium hydroxide. So if you have a halogenoalkane and you treat it with hot ethanolic or a strong alkali, like for example this potassium hydroxide, we can have sodium hydroxide, they both produce the same alkene. Yes, we get an alkene and no other organic products. So they are saying what is produced when T is treated with hot concentrated acidified potassium permanganate. Now we need to look at the monochloroalkanes. I can have the CH3, CH2, CH2, then CH2, what is Cl? Not so. Then the other one can be, that is 1-chlorobutane. Then I can also have 2-chlorobutane, CH2, then CH, I can put the chlorine here. Now putting a chlorine on this one is the same as putting it here. Another person may say the other one is CH3, then CH, then we put the chlorine here, then CH2, and then CH3. This one here is the same as this. These two are the same. So if I put it here, that means the numbering of the carbons is going to start from this end. So I will have 1, 2, 3, and 4. You see that? If I put it here, the numbering will then begin from this way, 1, 2, 3, and 4. Remember, this functional group must take the least number when you assign to the carbons. Now, when I look at what is happening here, I want you to look at that carbon that is having the chlorine. So it has how many groups? We can see a CH3, that is 1. There is this ethyl group, that is 2. There is chlorine, that is 3. And then there is hydrogen. So those 4 groups are different. That means this carbon here is a chiral center. That means it has 2 isomers, 2 optical isomers. That means that we are having 2 here, and then we are having 1 here. Now, those are 3, but here they say the 2 different monochloroalkanes. Are we there? That means we are not going to have these ones here. But we can also have another one. Okay? We can also have another one here. You see what is going to happen. Suppose I get CH3, then CH, and then I put the chlorine there. In fact, I can take off this hydrogen, and I say there is a chlorine here, then this one here. I have 2-chloro, 2-methyl propane. You see, hydrogens are 9, and the carbons are 4, then the chlorine. This one here, that is 1. Then I'm going to put off this one here, okay? And then I take this one and this one. Now what happens when we put hot ethanol potassium hydroxide, this carbon that is here holding the chlorine, it is going to lose that chlorine, and then an adjacent carbon to this one here is going to lose a hydrogen. So suppose this one loses a hydrogen, then we are going to have, actually let me take off this one here. So if we put potassium hydroxide in ethanol, and you hit the same thing here, in ethanol, and then you hit, we are going to get maybe CH3 here, C, then there will be a double bond. This will be a CH2. It is the one that has lost the hydrogen, okay? Then CH3. And even this one can lose, this one can lose, this one can lose. They will all give you the same product, okay? Then when we come to this one here, after this one has lost the chlorine, then this one can lose the hydrogen. You get it? So we shall have CH3, CH2, then another one is going to be CH. Now this one loses the hydrogen, so we shall have CH, then double bond, CH2. Now, when we put hot concentrated acidified potassium permanganate, we are going to see the double bond broken completely, and then oxidation takes place. So this one will give us CH3, C, O, and then CH3. This is what it is going to give us, okay? And then here we shall get CH3, then CH2, COOH. Here we get COOH, and then we shall also get the carbon dioxide there. Okay, but they are saying that they both produce the same alkene. You see that? And no other organic products. But when we look at this one, if they produce the same alkene, then that means they are supposed to give us the same product here. Okay, so that means I have to change this one here. So I'll take off this one here. Okay, I'm going to take away this one. I'm going to take off this one here, and then I bring in this other one here. I can take the chlorine from here, I take it to this one here, or any of these ones. Okay, so if actually we do that, I think it will come out. So if I have this one here and I put my chlorine here, then we put the hydrogen up here, hydrogen, and then CH2 Cl. So from here, when I put this potassium hydroxide in ethanol, this carbon here carrying the chlorine is going to lose that chlorine, and then this carbon here adjacent to this one is going to lose the hydrogen. Okay, so what are we going to have? We are going to have the CH3, then C, and then we shall have the CH3 here, then a double bond here, and then CH2. So do you see that it is giving us the same product as this one here, same organic product. This is product what? T, same alkene. You see that? So after oxidation, when we break here, we shall get methanoic acid here after oxidation, but then it will break down to give us the carbon dioxide, and then this one will give us the what? The ketone. So that means we are going to have CH3, C, then or CH3, then plus the carbon dioxide. And when we look at our answers here, it is option what? B. Then question 38, including structural isomers and stereoisomers, how many isomers are there for that compound there? Now we have carbon here. There is a double bond because there are two hydrogens, so I can have hydrogen, and then the two bromines are on one carbon. I can also have carbon, and then the two bromines are on the two different carbons here. Okay, but now you can see that each carbon in the double bond has gotten two different what? Groups attached to it. So that means here in alkenes we have what we call the geometrical isomerism and the stereoisomerism. Okay, that is the cis trans. So this one is the cis because these ones are on the same what? Side. Okay, same line. And then we can also have what? The trans. Bromine is here, and then it's also here, then hydrogen this way, and then here. So this one is going to be the trans isomer. So how many are they? There are 3. So that means our answer is going to be B. And then 39, they are saying which compound exhibits stereoisomerism. So stereoisomerism, here we are looking at geometrical isomerism, where this one happens in what? In alkenes. So the cis trans. Okay, and then we also have optical isomerism, where there is an existence of a chiral center. Okay, and then we get these non-superimposable images. Now let's look at this one here. 1-chloropropene. 1-chloropropene, I can have it as carbon here. It has the 2 chlorines on it, and then we have CH and then CH3. That would be the one. So here, because the 2 groups that we are seeing here are the same on this carbon atom, then we don't have what? Stereoisomerism there. Then we go to B, 2,3-dichloropropene. 2,3-dichloropropene. If I just bring this one here, 2, and then 3. So I'm going to put chlorine here, and then I put a hydrogen here. So there is a hydrogen here, and then there is a chlorine here. Okay, dichloro, 2 and 3. No, actually this will be 1 and 2. You see, on the first chlorine, then this one on the second one, but they said 2, 3. That means I'm going to remove this chlorine, and then I put it here. So this way I'll be having CH2, Cl, and then I can have a hydrogen here. Again, this one has 2, okay, 2 groups attached, so even this one is off. Then we go to the fourth one here. 1,2-dichloropropane. This is 1,2-dichloro. 1, 2, 3. When we look at all of these ones, what do we have? So there is a chlorine here, then H, and then another chlorine here, then hydrogen, hydrogen, and hydrogen. So 1, 2. You can see that this carbon here, okay, is connected to a methyl group. There is a hydrogen group here, then there is this other group here, and then this one here. They are all different. So since they are all different, that means this one here is a chiral center. And because there is a chiral center here, that means we can get stereoisomerism here, which is actually optical isomerism. Okay, so this is optical isomerism, which is under what? Stereoisomerism. So that is even, I think that is even our answer. But let's check D. 1,3-dichloropropane. 1,3-dichloropropane. We have 1, 2, 3. So 1 and then 3. That is where we are having the So if you look at all of these carbons, they are non-chiral centers. This one has the 2 groups. Okay, this one has the 2 groups that are the same, and even this one here. So we don't have here. That's why the answer is C. Then question 40, the mass spectrum of chloromethane shows a molecular ion peak at mass to charge value of 50 with the relative abundance of 18%. Other peaks are present in a mass spectrum. Now, when we see chlorine present, chlorine has 2 isotopes. Okay, we have chlorine 35 and there is chlorine 37. This one is 75% abundant and this one is 25% abundant. Then the AR of chlorine happens to be 35.5. So it is nearer to the 35 than to 37. That is why the value, that's why chlorine 35 is the most what? Abundant. Are we there? Now next, we are going to have a molecular ion peak. There is going to be not a molecular ion peak. The molecular ion peak actually represents the that mass you get there is for the whole molecule. Okay, but then this one, consider chlorine either 35 or chlorine what? 37. Now they are saying this one is at 50. 50 comes from where? This is 15, carbon is 12, then plus 3 for hydrogen, that will be 15. Then this chlorine here will either be 35 or 37. Now 35 plus 15 is the one that gives you the 50. That means we are seeing chlorine 35. So when you are drawing on the mass spectrum, we shall get 1 for chlorine 35, okay? And when you look at these ones here, when you try to check what I drew up here, this is 75%, this is 25%. 25 goes into 75 3 times. So that means you are going to have another peak here, which is a third, okay? Another peak is going to be a third of this one here. So if this is the M plus peak, then this one will be the M plus 2. Why are we saying M plus 2? It is because we have these 2 isotopes that differ by 2. Then for bromine, Bromine can be, bromine we have 79, and then bromine what? 81. These ones are all 50%. So for them, you will have the M plus 1 peak the same as the M plus 2 peak when they have the same heights, because it is 50%. You see that? So for chlorine, it has to be that. So if the relative abundance of this one is 18%, then we shall divide this by 3 to get the relative abundance of this one. So 18 divided by 3, you'll get 6 what? 6%. And they are saying here what is seen in the mass spectrum at mass to charge value of 52. So the 52 we are having there, chlorine 37, okay? So that is the M plus 2 here, chlorine 37. So it has to be 6%. And our answer becomes what? A B. So this has been it for this paper. Thank you so much for watching. May God bless you. If you find the content very helpful, kindly like, share, and even subscribe. See you in the next videos.